Hello students, my name is Mrs. Meetali Risbud from Fergusson College Chemistry Department. In the previous sessions, we have discussed some concepts in the topic solution. In this session, we will discuss few more concepts in the same topic. Let us move to PowerPoint presentation. Third colligative property which we have to discuss is the depression in freezing point. Now what is the freezing point? Freezing point of a liquid is the temperature at which the liquid and the solid are in equilibrium and the two phases have the same vapor pressure. See here, define freezing point. What is a freezing point? It is a temperature. This word temperature is important. तुम्ही लिहिताना असे लिहिता definition. It is a point at which is wrong. Remember, it is the temperature at which the liquid and the solid are in equilibrium and the two phases have the same vapor pressure. It is observed that freezing point of a solvent is lowered when a non-volatile solute is dissolved in it. The meaning of this is the freezing point of a solution containing non-volatile solute is lower than that of a pure solvent. Why? What is the reason? At the freezing point of a pure liquid solvent, the attractive forces among the solvent molecules are large enough to cause the change of a phase from liquid to solid. In solution, how solution is formed? By dissolving solute in a solvent. So in solution, the solvent molecules are separated from each other because of the solute molecule. Hence, the attractive forces between the solvent molecules decreases. Therefore, the temperature of the solution is lowered below the freezing point of a solvent to cause the phase change. Thus, freezing point of a solution containing a non-volatile solute is lower than that of a pure solvent. Now, if T0F is the freezing point of a pure solvent and Tf is the freezing point of a solution containing non-volatile solute, then Tf0 is greater than Tf. Why Tf0 is greater than Tf? We have discussed just now that freezing point of a solution containing non-volatile solute is less than that of a pure solvent. Means what? Freezing point of a solvent is more than that of a solution containing non-volatile solute. So the difference between the freezing point of a pure solvent and that of a solution, of course containing non-volatile solute, is called as depression in the freezing point. So the depression in the freezing point is shown by delta Tf is equal to what? Tf0 minus Tf. This is the variation of vapor pressure with temperature of a pure solvent, solid solvent and solution. Now here you can see three curves. Three curves are curve AB, isn't it? This is the vapor pressure temperature curve of a solid solvent. Then second curve is curve CD, which is the vapor pressure temperature curve of a liquid solvent. And the third curve is curve EF, which is the vapor pressure temperature curve of a solution. Now, curve AB and curve CD, they intersect each other at point B. So at this point B, the vapor pressure of a solid solvent and the vapor pressure of a liquid solvent are same. Therefore, the temperature corresponding to point B is what? Is Tf naught. So, Tf naught is the freezing point of a solvent. See here, the curves AB and CD intersect at point B. The temperature corresponding to B is the freezing point of a solvent Tf naught. Why this is a freezing point of a solvent? Because at this temperature, at Tf naught, the vapor pressure of a solid solvent and the liquid solvents is same. The curve EF and curve AB, they intersect at point E. So the temperature corresponding to point E is the freezing point of a solution Tf. So the temperature corresponding to this point E is what? Tf, which is the freezing point of a solution. Why? Because at this temperature, means at this point E, vapor pressure of solid solvent and vapor pressure of a solvent in a solution is same, and that's why Tf is the freezing point of a solution, freezing point of solvent in a solution you can say, or freezing point of a solution. The freezing point of a solution Tf is lower than that of a pure solvent T naught F. See here from the figure, temperature increases like this. See the position Tf and here Tf naught. So Tf is less than T naught F. So delta Tf is equal to T naught F minus Tf. This is the depression in the freezing point. Depression of the freezing point of a dilute solution is directly proportional to the molality of a solution. So delta Tf is directly proportional to m, where m is the molality. So delta Tf is equal to some constant. Let this constant be Kf into m, where Kf is the proportionality constant, but this is used in the depression of the freezing point. That's why it is known as freezing point depression constant, or one more word, क्रायोस्कोपिक कॉन्स्टंट. हा वर्ड लक्षात ठेवायचा आहे, क्रायोस्कोपिक कॉन्स्टंट. आपण एलिव्हेशन इन द बॉइलिंग पॉइंट तिथे केबी बघितलं होतं, त्याला इबिलिओस्कोपिक कॉन्स्टंट म्हणतात. इथं केएफ ला काय म्हणायचं? क्रायोस्कोपिक कॉन्स्टंट. नाउ इफ m is equal to 1, means when the molality is equal to 1, then we can say delta Tf is equal to Kf. So Kf is cryoscopic constant. So how to define cryoscopic constant? It is equal to delta Tf. But when? What is the condition? When the molality is equal to 1. That is, when 1 mole of a solute is present in 1 kilogram mass of a solvent. Thus, the cryoscopic constant is the depression in the freezing point produced by 1 molar solution of a non-volatile solute. That is, it is the depression in the freezing point produced when 1 mole of a solute dissolve in 1 kilogram mass of a solvent. Then unit of Kf. If we rearrange the equation, we can see Kf is equal to delta Tf upon m. Delta Tf, difference in the temperature, Kelvin. Capital T म्हटलं की Kelvin पाहिजे, so Kelvin. M molality, mole per kilogram. So which is equal to, unit is K kilogram per mole. Isn't it? Now, next point is the molar mass of a solute from freezing point depression. Let us consider a solution containing W2 gram of a non-volatile solute dissolve in W1 gram of a solvent. M2 is molar mass of a solute. Then moles of a solute, what is the formula? Moles of a solute is equal to mass of a solute divided by molar mass of a solute. Mass of a solute is W2 gram. So W2 gram divided by M2. M2, it is a molar mass which is expressed in terms of gram per mole. So W2 gram divided by M2 gram per mole. This gram will get cancelled and you will get some mole. Mass of a solvent W1 gram, which is same as W1 upon 1000 kilogram. The molality M of a solution is given by, what is the formula? M is equal to, in the previous session we have discussed what is the molality and formula for finding the molality. Molality is number of moles of a solute divided by mass of a solvent in kilogram. So denominator is mass of a solvent in kilogram, and that's why we have to convert this mass of a solvent in gram into kilogram. So molality M is equal to moles of a solute W2 upon M2, isn't it? W2 upon M2 mole divided by mass of a solvent in kilogram, that is W1 upon 1000 kilogram. So we can say that 1000 W2 upon M2 into W1 mole per kilogram. It is a molality, so unit is mole per kilogram. Now we know that delta TF is equal to KF into M. Therefore delta TF is equal to KF into M. What is M? This is our M. So 1000 W2 upon M2 W1. So M2 is equal to, let us rearrange this expression. Let us write the expression in terms of M2. M2 term. Let us shift this term to the left hand side and bring this delta TF term to the right hand side. When we change the side, this delta TF term will go in the denominator and M2 term will go in the numerator. So M2 is equal to 1000 into KF W2 divided by delta TF into W1. So if we know all the quantities W1, W2, then KF and delta TF, we can find the molar mass of a solute, where W1 and W2 are in grams, delta TF in Kelvin or degree Celsius, KF, unit of KF is K kilogram per mole, M2 in gram per mole, and the units of thousands are gram per kilogram. Remember this, units of thousand, gram per kilogram. So this is the relation between molar mass of a solute, which is the relation this M2 is equal to. So this relation is the relation between the molar mass of a solute and the freezing point depression. Parikshela, when only relation is asked, you have to write this relation. Of course, you have to write the meaning of the terms, what is W1, W2, KF, delta TF, M2, हे लिहायचं. If the question is derive relation, derive म्हटलं की हे सगळं तुम्हाला यायला पाहिजे. डेरिवेशन 2 मार्काला विचारतात आणि ह्या यूज द सेम टर्मिनॉलॉजी. अगेन आय एम सेइंग यू, मी मागच्या लेक्चर सेशन मध्ये पण सांगितलं, आत्ता पण सांगते की टर्मिनॉलॉजीज की सेम वापरायची. डोंट कॉल ए अँड बी, एम ए, डब्ल्यू ए किंवा एन ए, डब्ल्यू बी, एम बी, एन बी ह्या टर्मिनॉलॉजी वापरू नका. पुस्तकामध्ये जे दिलेलं आहे 1 and 2, नंबर 1 फॉर सॉल्व्हंट, नंबर 2 फॉर सोल्यूट, हेच लक्षात ठेवायचं. M2, M म्हणजे मोलर मास, सोल्यूटचं आहे त्यामुळे नंबर 2. सी हियर, मोल्स ऑफ अ सोल्यूट, सोल्यूटचे मोल्स म्हणजे त्याला काय म्हणणार की N2च म्हणणार आपण, आणि मास ऑफ अ सोल्यूट, मास म्हटलं की W, पण सोल्यूट आहे त्यामुळे W2. सॉल्व्हंटचा मास, मास म्हणजे W1, सॉल्व्हंट आहे त्यामुळे नंबर 1 द्यायचा. हे पक्क लक्षात ठेवायचं, नाहीतर अदरवाईज मार्क जातात. तुम्हाला वाटलं म्हणून तुम्ही MB म्हटलं किंवा MA म्हटलं असं करू नका. ह्याच टर्मिनॉलॉजी वापरा की ज्या पुस्तकात आहेत त्या. नेक्स्ट कॉलिगेटिव्ह प्रॉपर्टी विच वी हॅव टू डिस्कस इज द ऑस्मॉसिस. What is the osmosis? The spontaneous flow of solvent molecules through a semi-permeable membrane into the solution, or flow of a solvent molecules from a solution of lower concentration to a solution of higher concentration through a semi-permeable membrane is called osmosis. What is the osmosis? The spontaneous flow. Spontaneous flow म्हणजे काय? आपण ही घटना घडून येते without any external influence. So the spontaneous flow of solvent molecules through a semi-permeable membrane into the solution, or the flow of a solvent from a solution of a lower concentration to a solution of higher concentration through a semi-permeable membrane. Now see here, what is a semi-permeable membrane? Semi-permeable membrane is a membrane which allows only the solvent molecules to pass through it, but not the solute molecules. It is a membrane which allows the solvent molecules, but not the solute molecules to pass through it. There are two types of the semi-permeable membrane: natural semi-permeable membrane and artificial semi-permeable membrane. Natural semi-permeable membrane is cellulose, animal bladder. Artificial semi-permeable membrane is copper ferrocyanide deposited in the pores of a porous porcelain pot. Have you followed what is a semi-permeable membrane? Now, see here again, osmosis. The spontaneous flow of a solvent molecules through a semi-permeable membrane into the solution. See here, see the figure. Solvent and solution separated by this semi-permeable membrane. So when the solvent and solute are separated by a semi-permeable membrane, we observe a spontaneous flow of a solvent molecules into the solution, see, through this semi-permeable membrane. This is a unidirectional flow. Solvent molecule passes into the solution through this semi-permeable membrane. Now the other half part of the definition, or the flow of a solvent from a solution of a lower concentration to a solution of a higher concentration through a semi-permeable membrane. See here, solution of a lower concentration. This is a solution of a higher concentration. The two solutions are separated by semi-permeable membrane. So, as the two solutions are separated by this semi-permeable membrane, there we observe a spontaneous flow of a solvent molecules from a solution of lower concentration to a solution of higher concentration through this semi-permeable membrane. Now, if the question is define osmosis, you have to write this whole definition. Don't write the definition like this: the spontaneous flow of a solvent molecule through a semi-permeable membrane into the solution. That's it. No, which is wrong. Or this also you have to write whole definition, or the flow of a solvent molecules from a solution of the lower concentration to a solution of higher concentration through a semi-permeable membrane. हे दोन्ही मिळून दोन्ही पॉइंट्स यायला पाहिजे डेफिनेशन मध्ये. We have discussed this semi-permeable membrane. Now this is a simple experiment which demonstrates the osmosis. The outer egg of the three eggs are removed. This is the normal egg. The egg, this is the egg which is kept in the normal water, and this is the egg which is kept, this egg is kept in a salt water. Now compare the size of the egg. हे normal egg आहे. हे egg कशामध्ये ठेवलंय? नॉर्मल वॉटर मध्ये. सी द कंपेअर द साइज. काय झालाय? देर इज इन्क्रीज इन द साइज. सो वी कॅन से द एग स्वेल्स. कंपेअर द साइज ऑफ दिस टू. हे एक कसं झालंय, कंपेअर द साईज, दिस एक इज रिड्यूस इन द साईज, काय म्हणतो आपण त्याला, श्रिंक. दिस egg is kept in a salt water. Now the egg membrane is semi-permeable in nature. So when the egg is kept in normal water, water हे एक मटेरियल मध्ये जातं आणि त्याच्यामुळे एक काय होतं, स्वेल्स होतं. त्यामुळे देर इज इन्क्रीज इन द साईज. egg kept in a salt water. आता एक मधलं जे काही वॉटर मोलेक्युल्स आहेत, सॉल्व्हंट मोलेक्युल्स, ते ह्या सॉल्ट सोल्युशन मध्ये जातात आणि त्याच्यामुळे एक कसं होतं, साईजने कमी होतं किंवा एक श्रिंक्स इन साईज. Then the next point is osmosis and osmotic pressure. Now this is an experiment to show the osmosis. Now this figure is taken from your book, whereas in this figure, see here, solution and the solvent both are shown by the white colors, and that's why this figure is taken from some other books. Here you can see the difference in the color of a solvent and solution. So in order to clear the concept, I have taken this figure. म्हणजे दुसऱ्या बुक मधली कुठली तरी फिगर घेतलेली आहे की जेणे इथं कलर डिफरन्स आहे, त्यामुळे तुम्हाला सोल्युशन आणि सॉल्व्हंट ह्याचं सेपरेशन कळेल. नाउ a semi-permeable membrane is tied over the mouth of a thistle funnel and it is filled with a sucrose solution of some concentration and is immersed invertedly in a beaker containing a distilled water. So this is a thistle funnel. The mouth of this thistle funnel is closed by a semi-permeable membrane. Here also this is a mouth of a thistle funnel which is closed by a semi-permeable membrane. It is cellophane paper is used as a semi-permeable membrane. And this thistle funnel is filled with a sugar solution. Here also a sugar solution is taken in this thistle funnel. This thistle funnel is inverted in a beaker containing a water. So this is water, this is a sugar solution. Here this is a water, beaker मध्ये हे water आहे आणि हे काय आहे, sugar solution आहे. Now see here, water म्हणजे solvent आहे, thistle funnel मध्ये solution आहे. So solution and the solvent separated by what? Separated by a semi-permeable membrane. Here also solvent आहे आणि solution आहे, मध्ये काय आहे, semi-permeable membrane. So as a result, what happens when a solvent and solution are separated by a semi-permeable membrane? काय होतं, osmosis होणार. So as a result, some of the solvent molecules passes through the membrane into the solution. Solvent molecule ह्या membrane मधनं solution मध्ये जाणार. Some of the solvent molecules passes through the semi-permeable membrane into the solution. And due to this, the liquid level in the tube, in the stem of the thistle funnel increases, or we can say rises. Here in this figure you can see here initial level. When osmosis takes place, there is increase in the level, so level rises. Now so the liquid level in the tube rises and hydrostatic pressure arises from column of solution. Now this hydrostatic pressure, which is given by H rho G. This hydrostatic pressure pushes the solvent back into the solvent through the semi-permeable membrane. Here the hydrostatic pressure pushes the solvent back through the membrane into the container. The developed hydrostatic pressure pushes the solvent molecules, of course from the solution, back into the solvent through the semi-permeable membrane. The column of the liquid in the tube rises continuously and eventually stops rising. Now at this stage, the height of the liquid means at which stage? At the stage at which the height of the liquid column in the tube remains constant, the hydrostatic pressure developed is sufficient to force solvent molecules back through the membrane into the container at the same rate as they enter the solution. So here an equilibrium is established. So an equilibrium is established where the rates of forward and reverse passages are equal. Now what is osmotic pressure? The hydrostatic pressure that stops, this is very important, that stops the osmosis is an osmotic pressure of the solution, which is denoted by pi. What is osmotic pressure? It is the excess pressure which stops the flow of solvent molecules into the solution through semi-permeable membrane. What is osmotic pressure? It is the excess pressure which stops the flow of a solvent into the solution through semi-permeable membrane. The hydrostatic pressure is equal to H rho G. What is H? H is the height of the liquid column in the tube. Rho is the density of a solution. And G is acceleration due to gravity. Isotonic, hypertonic and hypotonic solutions. Isotonic solution. Two or more solutions having the same osmotic pressure are said to be isotonic solutions. So what are the isotonic solutions? Two or more solutions having the same osmotic pressure. Iso, the meaning of the word iso means same. मग काय same असतं? Osmotic pressure same. So two or more solutions having the same osmotic pressure are said to be isotonic solutions. Then hypotonic solution, hypo म्हणजे काय? Less, कमी. So if two solutions have unequal osmotic pressure, the more dilute solution with lower osmotic pressure is called hypotonic solution. So what is hypotonic solution? If two solutions have unequal osmotic pressures, then the more dilute solution with lower osmotic pressure is a hypotonic solution. Hypo म्हणजे कमी. अजून एक गोष्ट याच्यावर लक्षात येते, द मोर डायल्यूट सोल्युशन विथ अ लोअर ऑस्मोटिक प्रेशर. म्हणजे काय कळतं की डायल्यूट सोल्युशन असेल तर ऑस्मोटिक प्रेशर कसं असतं? लो असतं, कमी ऑस्मोटिक प्रेशर. देन द नेक्स्ट इज हायपरटोनिक सोल्युशन. हायपर म्हणजे काय? जास्त, मोर. सो इफ two solutions have unequal osmotic pressure, the more concentrated solution with higher osmotic pressure is called hypertonic solution. Hello students. So in this session we have discussed freezing point, depression in the freezing point. We have discussed the relation between freezing point depression and molar mass of a solute. We have discussed also the osmosis, then concept of osmotic pressure. We will continue the remaining part in the next session. Thank you.